Hi, everyone. I'm running a little bit late. My apologies. Had a little bit of a tech problem here, but I think I got it fixed. Hope everybody's doing okay. Just a quick reminder that Tuesdays from this point forward is just be the last chapters, which we got two. And then Thursdays will be a study day. Good time to come in and bring in questions. Okay, and like I said, you're welcome also to come to my 415 class. There's no problem in that. I'm doing the same thing, having Thursdays being a study day. So if you have a lot more questions, bring them during that time session. If not, those days times don't work for you, send me an email and I'll see what I can do as far as making time for some questions you may have. So the plan, we're on chapter 14. It's about 30 some slides. We will do that today and next Tuesday. And then the following Tuesday, we'll end it up with chapter 15, which is a very short chapter. And that will get you ready for exam number 5. Okay. So that means that, then let me look at the calendar here real quick. Today's the 17th, so I'll do 14 today. The 24th of November, we'll be doing the rest of 14, chapter 14. We don't have class the 26th. That is Thanksgiving. And then we come back on the 1st of December, and we'll finish up the final chapter. And if we need to, we can go into the 8th, the following Monday, which Tuesday, I mean, if we need to. I don't foresee, but if we do, we can use that time. Otherwise, the 3rd, the 8th, and the 10th is basically your time. You got questions, come here. I'll be here, but obviously not doing a lecture on any of the chapters, but it'll be open for any questions on those days. And then we have, I believe, the 15th. The 15th is for the final. Now, there is a practice final exam on the course website. I believe there's also a review sheet with respect to the final, which is comprehensive, meaning all the chapters, 1 to 15. You can look at the old exams on the website. Again, that will give you an idea about the type of questions, but to be very similar to the exam questions we had in the past. Obviously, the numbers will be changed a little bit, but basically the same format. Okay? So, any questions about that? Feel free to send me an email if you have any other questions. Okay? So, let me get started with chapter 14, which is intermolecular forces. Okay, now here in this particular chapter is a couple things you need to go back and refresh your memory. One is polar bonds. Remember, we talked about polar bonds. They were covalent bonds, and they were polar because point number 1 was that bond between the two atoms, they were different. Okay, just the fact that they were different meant you had a polar bond. Okay, with one exception, which was carbon-hydrogen. The bond there, the two atoms are basically treated as the same atom. Why? Because the electronegativity, for example, we talked about that, where fluorine was the most electronegative element, and we use that as a benchmark to determine which atom was more electronegative that is not fluorine. So if we looked at carbon-nitrogen, nitrogen is closer to fluorine, so nitrogen was more electronegative. So if there was a bond between carbon and nitrogen, it would be polar because they're two different atoms, and 2, because nitrogen is a lot more electronegative, it would pull the electron density toward the nitrogen, giving us a polar bond, where one end had a partial positive side and the other end had a partial negative. Okay, so we talked about those polar bonds, and then we talked about molecules. How does the polar bond affect the molecules? Well, in general, when you have all non-polar bonds. That is atoms that the electronegativity is essentially the same, okay? And so all the diatomic compounds, carbon-hydrogen bond, all those are non-polar bonds, and therefore in a molecule, they would have a non-polar overall molecule, okay? So that part is important here because we need to recognize whether a molecule is polar or non-polar. The other aspect with respect to polar bonds in a molecule was this. Again, in general, when you had all polar bonds, you had a polar molecule unless the polar bonds cancel each other out. Remember, we had a dipole arrow. We designated which direction the dipole was going. The point was going to the most electronegative element, and the tail end of the arrow was pointed toward the partial positive or the least electronegative, okay? And those arrows can be treated as quantities. If those arrows are going in the same direction, they are additive, okay? If those dipole arrows are going in opposite directions, they cancel each other out, and therefore is the polarity of the bond is canceled out. Therefore, you end up with a non-polar molecule. For example, to refresh your memory, carbon dioxide. We go back and check your notes. You'll see that carbon dioxide had two polar bonds. It was a carbon double bonded oxygen on one end and a carbon double bonded oxygen on the other end. This is all related back to the Lewis dot structures. You see how everything is all tied in together? We had to use Lewis dot structures to come up with a structure, okay? And in carbon dioxide, the dipoles were opposite of each other and they canceled out. Also, you have polar bonds that were in a tetrahedral configuration. Here we go with the shapes. Go back and review the shapes table. If they were in a tetrahedral configuration, in that configuration, all the dipoles, if you had a polar bond, four of them, for example, say carbon tetrachloride, you have four dipole bonds with carbon and chloride, but they're all in the tetrahedral configuration and they cancel each other out. If I remove one of the chlorides from the four chlorides and put something else in, then now we have a polar bond because the three remaining polar bonds do not cancel each out equally, okay? So we went through that in that chapter, so go back and refresh your memory. Why do we need to know that? Because this is where we put all that together and talk about intermolecular forces. Intermolecular forces, the prefix INTER, deals with forces amongst other molecules. In contrast to intra, INTRA, which that deals with the actual bonds within the molecule, okay? And so with the actual bonds, we either have a covalent bond or ionic bond, and of the covalent bonds, we either have a nonpolar or a polar bond. Those are the intramolecular forces. The intermolecular forces, and that's how molecules affect each other, is dependent on the type of polarity of the molecule. And that's why things like honey, for example, is very thick and very viscous compared to water, okay? Because we know that we have a cup of honey and a cup of water, and we empty those cups, the water is going to flow much quicker than the honey. And that is because the intermolecular forces of the honey molecules are very strong, and they hold on to each other strongly, much more so than the intermolecular forces of water. And the result being that the honey would be a lot more viscous. Now you think about this for a second. All right, so how can I make that honey flow quicker? What do? We heat it up. So we heat up the honey, which makes it less viscous and allows it to flow as much as water does. And what we're doing by putting energy into the system, we are breaking up those intermolecular forces between the molecules of the honey, making them less interacting with each other and the effect changing the viscosity. The same is true for things like boiling point. Water boils at 100 degrees, where let's say ethanol or alcohol, drinking alcohol, boils around, I believe, 78 degrees Celsius. Okay, so we got something that boils at 78 degrees Celsius, something that boils at 100 degrees Celsius. Just the fact that they have different boiling points tells you that the intermolecular forces of water is much stronger. Okay, because it takes a lot of energy, a lot more energy to break those forces apart to cause the liquid water to go evaporate and go into the gas phase. As compared to ethanol, those intramolecular forces are much less. And I only need to go up to 78 degrees Celsius in temperature to put enough energy to evaporate or to boil the ethanol away. You're familiar with nail polish remover. That's a molecule called, a compound called acetone. Acetone, as you open that bottle, you can see, you can sense the material just you literally evaporate. Again, if I compare water, ethanol, and acetone, acetone's intramolecular forces are much, much more weak. And therefore, those molecules are not held on to each other very well. They don't interact very well. They don't take, I shouldn't say very well, it doesn't take much energy to break up what interaction they have. So they become volatile and evaporate at a much lower temperature than water that requires you to go all the way up to 100 degrees Celsius. Okay, so these forces are, and all these forces that we're going to talk about, there's only 4 of them, are a function of the polarity of the molecule. So that's why it's crucial and important that you review about polarity. Okay, so excuse me. Here's a molecule, and it's a diatomic molecule. You can see here that we got this blue colored elongated molecule, and they are interacting with each other. And so we do is we actually, put a dotted line. There's an interaction going on there, because remember that everything around us is electrons. Electrons are governing everything about chemistry. And we got this electron around the item on the left, and those electrons are moving. So at one point in time, it could cause to have a partial positive part, okay, which then causes the other molecule to be attracted to it. You ever wondered why you take a balloon and you rub it on your head and then you put it on your chest? Why does it stick? Okay. Why does a balloon, think about this, if you have one at home, try it. Get a balloon, blow it up, rub it on your head or someone else's head, doesn't make any difference. And then take that balloon and put it on the surface or put it on your chest. Doesn't it stick? And if it doesn't, you rub it again on your head some more, right? And it's put it on, and it sticks to your shirt. Why is that? Is it some Harry Potter magical stuff going on? Anybody have a guess?
No, it's just like static or electron activity.
Okay. You're on the right track, and that is correct. Static electricity, which anybody know what static electricity is made up of? We have it around the all the time. You wake up with a bad hair day, your hair frizzes out. Or you rub your feet on a carpet as you walk, and then you touch something, you get zapped. What is static electricity? Anybody know what that is? Electrons. Those crazy electrons again. They're just free roaming electrons. Okay. And as you rub your feet on the carpet, you're building up your electron density. You're building up an electric charge. You become negative, a lot more negative than you normally would. And then you touch something that has more of a positive side to it. And guess what? Energy goes from a high to low. High electron density, the partial negative on your body. An object now has its electron density is much less, so it has a net positive, and electricity shoots by, or electrons, and you get zapped. Same with the balloon. Similar with the balloon, I should say. You take that balloon, you rub it on your head. Your hair is loaded with electrons. Okay, these electrons get transferred to the balloon. So that surface of the balloon now has a high partial negative charge to it. Okay. Now, as you bring it toward your body, there are on the surface of your shirt, on your surface and anything, again, electrons. Okay, you got high electron density on the balloon, and you bring it toward the electron density on your shirt. Well, negative repels negative. Remember that? Okay, so those electrons on your shirt, on your body, are kind of pushed back into your body a little bit, resulting in a partial positive area on your body. There's electrons there, but as far as much as they had before, not as much. So you create this temporary hold between the balloon and your chest. Eventually, the balloon will equilibrate and fall off your chest as soon as the electrons go back to a stable state. So those electrons have a lot to do with chemistry all around us. Okay, so when we talk about intramolecular forces, as far as strength is concerned, they're relatively weak. A bond is much stronger. An actual chemical bond is much stronger than these intramolecular forces. Okay, and they could be easily be manipulated, or they're not as strong as an actual chemical bond. All right, so let's take, for example, hydrochloric acid. Okay, now hydrochloric acid, we know, has a dipole. Okay, in that bond, we know that dipole arrow goes from the hydrogen to the chloride. Why? Because the chloride has a higher electronegativity than hydrogen. And so the electron density is pulled toward the chloride in that bond. Okay. Another molecule adjacent to it, similar situation. Okay. And so what we have created, and I can't really make the partial symbol, but I'm just going to put the hyphen. So it's just a partial negative and the partial positive, okay, that's been created. And so as negative and positive, they attract each other. So we have this interaction that's occurring. Those are the intermolecular forces between molecules. Now, this is two-dimensional. We're just showing you in 2 dimensions. But keep in mind, nature's 3-dimensional. So this is happening not only in the X and the Y, but in the Z coordinate. And so it's all around the molecules. And that is not just in one direction. Okay? So that is the intermolecular forces that we're dealing with and working with. Those are the interactions between the molecules. Okay. Now there's 4 types. 4 types. And it's really interesting considering, remember, we talked about chemical bonds. There's only 6 types of chemical bonds of all the chemicals that are made out there. And now when we talk about intermolecular forces, there's only 4 types. The first one is called London dispersion forces, or LDF. Now, the thing to remember about this is any molecule that is non-polar, okay, any molecule that is non-polar, so that incorporates carbon-hydrogen bond and all the diatomic molecules, and any compound that has polar bonds but they get canceled out. So any molecule that is non-polar will the only force they have, the only intermolecular force they have are the London dispersion forces. The second type is called the dipole-dipole forces. And that, a good example is the previous one we just did with hydrochloric acid. And so here we could say that any polar molecule, okay, I should have wrote molecule up there. So polar molecule because we're not just talking about the bond, we're talking about the whole molecule. So any polar molecule, their intermolecular forces are that they have are the dipole-dipole forces. Okay. Now there's a special type of force for only a limited molecules. We call that hydrogen bridging forces. Sometimes you might see literature call it hydrogen bonding forces. It's not a true bond. You can see from that diagram we had that dotted arrow between molecules. It's just an attraction. So the name is slowly being converted and changed over to bridging rather than hydrogen bonding. So, but you may still see it pop up, hydrogen bonding forces, but use the preferred term hydrogen bridging forces. Now, point one, it's a dipole molecule, but only molecules that have hydrogen bonded to nitrogen, oxygen, and fluorine. Okay. So one, let me write that down. Obviously, it's a polar molecule. But only those that are bonded to nitrogen, only those hydrogens bonded to a nitrogen, or a hydrogen bonded to an oxygen, or a hydrogen bonded to a fluorine. Okay, and we kind of use the NOF. I call it not on file, but NOF, nitrogen, oxygen, and fluorine, okay? And hydrogen bridging, hydrogen, the term there speaks for itself. Those are hydrogens bonded to nitrogen, oxygen, and fluorine. So yes, they are polar molecules. Yes, there are dipole forces for number 3. However, because of the interaction between the hydrogen, the nitrogen, oxygen, and fluorine, which is much stronger, they have their own special force, okay? And so it's called hydrogen bridging forces. Now, the final one is called ion dipole forces. Now, the key word there is ion, okay? So if we break that down, think about this for a moment. You know, when we talk about ions, we're talking about aqueous systems. So normally we're talking about, you know, all those ions that we talked about and whether things were soluble. Even those that are insoluble had a little bit of ions in solution. And so when we talk about ion dipole forces, the criteria here, that one is it's got to be an ionic compound and an aqueous system. Normally that, you know, that's going to be obviously water, okay? So any of the salts in a water system, an aqueous system. And the only force involved there is called ion dipole. Has nothing to do with 1, 2, and 3, okay? 1, 2, and 3 deal with covalent compounds. Number 4 deals with ionic compounds and the aqueous system, in which in this case should be water. Okay, Now, with respect to strength, and when we talk about strength, amount of energy to break that interaction, we're looking at 1 being the weakest. It's going to be a relative strength here, and then followed by 2, a lot more stronger than 1, and 3, much more stronger than 2 and 3. When we talk about strength, we're just going to deal with 1, 2, and 3, because in number 4, it's extremely strong. If you ever take sodium chloride in water, that's a good example of ion dipole force. To make salt water, okay? You evaporate the water, you end up with salt, solid salt. That's how that happens. But while it's in solution, while the water is in there, the only force is the ion dipole forces involved there. Okay. Let me clear this up and move on. So we got 4 intermolecular forces. Okay, let's talk a little bit about London forces. These tend to be temporary. They don't last for long. Very similar to the balloon situation, where, you know, I transfer those electrons onto the balloon and put them on the surface of my chest. Okay, they hang there for a little bit, but eventually they will dissipate and go back to their natural state. Nature doesn't like to stay up. By transferring those balloons, we put them into not the stable state. So eventually, the whole system goes back to its stable state. So these are temporary, and there's attractions between nonpolar molecules. Okay, that's what I mentioned earlier. Nonpolar molecules, diatomic, carbon, hydrogen, or any molecule that has all their dipoles cancel out. Dipole bonds cancel. Okay. Now electrons are pushed to one side, so the result is there's a temporary partial negative charge, just like the balloon analogy I used. And eventually they will dissipate, but there's enough interaction back and forth that they get an attraction. Okay. Some molecules that are nonpolar is much greater than others. You're well familiar with this. If you take, let's say, vegetable oil and you compare it with lard, okay, what is the main difference that you see? If I were to tell you that they were both basically carbon hydrogen bonds, okay, but what is the difference between the vegetable oil and the lard? Physically, what do you see there?
The lard is more solid.
Exactly. The lard is solid, just like a stick of butter, okay, if we're using, you know, real butter. And the vegetable oil, it's liquid. Now, they're both made up of nothing but, well, the majority of it is made up of carbon, hydrogen. And we would say, okay, well, we got London forces very weak. However, the lard has a lot, they're bigger molecules, so they have a lot more London forces, and therefore the net result, there's a lot more interaction. The these chains of hydrocarbons are longer, and so more force involved, resulting in a solid material versus the vegetable oil, where yes, there are London forces, but not as much as that from solid lard. Okay. And what do we do even with a stick of butter? What do we do when we stick it in the pan? We warm it up, right? What happens? It liquefies. It liquefies because the interaction, the heat, the energy that it absorbs is breaking up the interaction. And just like the analogy of the honey, is breaking the interaction between the molecules and then allowing it to liquefy. Okay. All right. So bigger molecules, more electrons, more London forces. That's what the last point was meant. So that's why you see solid lard versus liquid vegetable oil. Yes, there's some other factors, but in general, right now. This diagram kind of shows you what's happening. We get 2 nonpolar molecules kind of come together. the electron density kind of from one pushes it away from the other, where we create a temporary partial negative side and a partial positive side, much like the balloon analogy. Okay, but they're very weak. Okay, and they're easily taken care of as far as breaking them apart. Now, the other one, number 2, was the dipole force, intermolecular force. And first of all, they're not temporary. With respect to these partial positives, there are a temporary partial positive and a temporary partial negative. With respect to dipoles or any polar bond, those are permanent dipoles. They're permanent because one of the partners in that bond has a higher electronegativity. And so it will have a permanent partial negative and a permanent partial positive side. Okay, so here in this diagram, you can see that dotted line is that intermolecular force interaction between the molecules. In this case, hydrochloric acid. Okay. They're much stronger than London forces, as I mentioned earlier. They must be polar molecules. Okay. And so if the molecule is not polar, then there's no dipole forces. If they're not polar, they must be nonpolar, therefore London forces. All right. Now, hydrogen bridging. This is the exception, not the exception, the additional force that there is between the interaction of hydrogen when it's bonded to fluorine or fluoride, oxygen, or nitrogen, NOF. Okay, that hydrogen bridging attraction is, you can see here by the diagram, you have the water molecule, which actually has a double positive, partial positive side, and then that interaction between the hydrogen of another water molecule. Now, keep in mind, we live in a three-dimensional world, so this is happening three-dimensionally. This particular force is very, very strong, okay, as compared to dipole forces, as compared to London forces. Okay. And of course, again, these are intermolecular forces, interactions, they're not bonds. So with respect to an ionic bond or interaction or a covalent bond, they're much, much weaker in that. But with respect to the through intermolecular forces, they're the stronger of the IMF interactions. The ion dipole force. Again, we're dealing with an aqueous system, okay? We have a polar molecule, which 99.9% of the time is water, okay? And then we have a fully charged ion, which means we have an ionic compound. And so if you look at that picture there, you can see you get the sodium ion with a full-fledged positive charge, and it's being solvated with the water molecules, because the water molecules have a very strong permanent dipole of a partial negative. And therefore, the sodium is surrounded by all these water molecules, the oxygen in the water molecules surrounding the ion, okay? On the other end of the spectrum, if you can imagine the chloride with the full negative, if this was sodium chloride, then the chloride would be totally solvated by the partial positive side of the hydrogen of water, okay? So they would be someplace up in here. So, all right. So let's do a quick summary. Bonds versus the forces, okay? We talked about bonds. We had a whole section about bonds, all right? We have an ionic bond, which is a bond or a interaction between a metal and a non-metal. And we're talking about a full-fledged charge. So we got sodium chloride. Sodium has a full-fledged charge positive. The chloride has a full-fledged charge negative, okay? Then we had covalent bonds. These were bonds between two nonmetals. And within the covalent bonds, we had two subcategories. Okay. One was polar covalent bond, which was an unequal sharing of that bond, an actual physical bond. Okay. Unlike the ionic bond, which basically are two magnets coming together, a covalent bond is actual sharing of the electrons between two different atoms. And if you had an unequal sharing, then you had a polar covalent bond. Okay. If you had equal sharing, then you had a non-polar covalent bond. All right. All right. So I need to answer this phone call real quick. Give me 1 second. Okay. Is everybody's connection okay? It looks like Amanda's connection is a little choppy. I did have a signal that popped up, said my connection was a little bit not the best, but it went away. I'm checking my electronics right now. Everything's, yeah, it could be your internet. There's a possibility right now. It's really, the bandwidth is really getting hit hard overall. Okay, so where was I? Oh, thank you for that quick stop here. I had to answer that phone call. All right, so we had polar covalent bonds and non-polar covalent bonds. Okay, so those are separate. Those forces are separate between the IMF interactions. Okay, IMF forces. We have London forces, which deal with non-polar molecules, and then we have dipole-dipole force, which deal with polar molecules. And then we had a special force called hydrogen bridging force. And that was only for those that have hydrogen bonded to either nitrogen, oxygen, and fluoride. Okay. And then the last one was the ion dipole force. And again, that dealt with an aqueous system, which was water and a ionic salt of some sort. Okay. All right. Yes, 14 I'll probably be doing today and next Tuesday. The question was about chapter 14, this one we're doing, because we are on slide 14 and we're about halfway there. All right. Now, let's go through some examples here. And they're asking you the question, indicate the strongest IMF in samples of these molecules. Okay, now, in order to answer these questions, you really have to go back to the Lewis dot structures. Okay, coming back to Honshu, right? Well, I keep emphasizing this is the stuff, you got to learn it because it's going to come around, and here we are. Okay, now, if you look at your notes, you will see that carbon dioxide, we came up with a structure that had oxygen bonded to carbon, double bonded to oxygen. Okay. All right. Now we can see that carbon and hydrogen, two different elements, therefore a dipole, a polar bond. And now we look up carbon and oxygen in the periodic table, find out which is more electronegative. And we determine that oxygen is the more electronegative because it's closer to fluorine. So the dipole arrow goes from carbon to oxygen. And the same is true in the other direction, okay? And both sides have a double bond. So the magnitude of those bonds, they are going in totally different directions. So the one to the right is going in the positive direction. The one to the left is going in the negative direction. And the result is they cancel each other out, okay? They cancel each other out. And the reason, somebody asked me, why is it that the arrows cancel out? Well, I'm not gonna get too much in detail, but I can tell you this. Those dipoles are what we call vectors, okay, just very temporarily. Vectors are a mathematical function, I guess, or mathematical entity that give you both direction and magnitude. So that arrow represents X amount of something, and that arrow tells you which direction you're going, normally relative to a 0 point. Okay, so if we were graphing that arrow to the right, it would start at 0 and is going in a positive direction. If we're graphing that arrow to the left, it starts at 0, but it's going in a negative direction, okay? That being the case, the fact that they're going in opposite directions, we could graphically say they cancel each other out. If the arrows were going in the same direction, they're cumulative. So whatever force that may be would double, okay? All right, and so that's in a nutshell what these dipole arrows mean. So graphically, if you can see that they cancel each other out, boom, we have a nonpolar molecule. So carbon dioxide, though it has two polar bonds, okay, is nonpolar. The fact that it's nonpolar automatically tells you the only force of those three forces, it's not ionic, right? Carbon dioxide is not an ionic, so it cannot be the ion dipole, okay? We just went through the scenario of finding structure, what we did in the previous chapter, but we kind of refreshed our memory on it. And the dipoles cancel each other out. The bonds cancel each other out because they're polar bonds. They cancel each other out. Therefore, you end up with a nonpolar species. So it's not an ion. It is no dipole interaction going on. There's no hydrogen here to bond it to nitrogen, oxygen, or fluoride. So we can eliminate those forces. We eliminate the dipole, eliminate the ion dipole, eliminate the hydrogen bridging. So the only force left to deal with is the London dispersion forces, okay? That's the only force that it has. So it's a very weak force, okay? Now, if we do the Lewis dot structure for PF3, remember how we did that? We count up all the valence electrons for phosphorus, all the valence electrons for the fluoride, okay? Phosphorus is the central atom. And when we do that, you will find that there is a lone pair on the phosphorus, because it's on group 5, and I mentioned way back when that group 5 molecules will always end up with a lone pair on that central atom. And whenever you end up with a lone pair on the central atom, it squishes the other bonds down because those lone pairs take space. The net result is you can, as a general rule, say, I got a polar molecule simply by the fact that I get a lone pair on the central atom, okay? And for oxygen, which is the next group over, they end up with 2 lone pairs, so it's definitely very polar. And so PF3, phosphorus trifluoride, is very polar, okay? And so obviously London forces is eliminated because it's a polar molecule. We can eliminate ion dipole because there's no ions involved here. So it's the second force we can eliminate. We can eliminate hydrogen bridging forces. Why? Because there's no hydrogen here, right? All right. So the only thing left is dipole-dipole. Okay. Notice the process of elimination until you become comfortable just looking at it and determine what force you're involved with. So go through a process of elimination based on what you know and break it down. Okay, here we have HF, linear species. It's simply, if we do the Lewis-Dot structure, you'll find that you have 3 lone pairs around fluoride, okay, and then 1 bonded pair with the hydrogen. Okay, so we have a linear species. Hydrogen, fluoride, the fact you got fluoride automatically tells you I got a polar compound, plain and simple. Fluoride is the most polar element there is. So very polar, okay? Now the question is, all right, well, let's go through the elimination process. Ion dipole, we can eliminate that, okay? We can eliminate London forces because it's polar, and London forces are only good for nonpolar. And so we got 2 choices now. We have the dipole, and we have the hydrogen bridging. Now, you look at dipole. Yeah, I got a dipole there, so I could say dipole. However, we have hydrogen bonded to fluoride. Okay, so it's part of the not on file, NOF. That means that hydrogen bridging is the stronger interaction than the dipole interaction. Okay, so hydrogen bridging force is the strongest intermolecular force involved for HF. Okay, second one, or fourth one, I should say, carbon hydrogen. The fact that you see nothing but carbon and hydrogen, which is again a hydrocarbon, and I mentioned that any carbon hydrogen bond can be treated as nonpolar, and we got 4 of them here. And so 4 nonpolar bonds result in nonpolar compound. Okay. Nonpolar compound, automatically the London dispersion forces. All right. Then finally down at the bottom, the last one, you got Ki. Recognize you're dealing with an ionic compound. Point number 1. Point number 2, you got AQ down there in parentheses. That's a state, which tells you I'm in an aqueous solution. Okay. So those 2 points, you totally eliminate London forces, dispersion force, dipole, and hydrogen bridging. You're simply dealing with a ionic or compound interpolar bond, and the force you're dealing with is simply the ion dipole. Okay. Now, with respect to properties, all right, the London forces, let's take, for example, boiling points. Okay. Those with the weakest force will have the lowest boiling point. The boiling point is that temperature in which at 1 atmosphere, the compound goes from a liquid to a gas phase. Water, as I mentioned before, boils at 100 degrees. Okay, different things have different boiling points. So here we could say this, it's a relative, we can't give you specific numbers, but we can say this. Those with London forces, which is carbon dioxide and methane, would have the lowest boiling point. The next one up, with the next lowest point, if you look at it that way, will be the one with the dipole force, okay? And the one with the highest boiling point will be the one with the hydrogen bridging forces. So HF would have a higher boiling point than the other 3. And carbon dioxide and methane would have the lowest boiling point compared to the other 2. And phosphorus trifluoride will be somewhere in the middle, okay? And that's just for boiling point, because we're going to use this to predict. We do a comparison between, it's all we can do, compare between 2 molecules. Well, not only are we going to compare boiling point, we're going to compare what's called surface tension. Okay, we're going to compare viscosity, and one more here, and I haven't seen your moment. We got boiling point, vapor pressure. Excuse me. Those three properties that we're going to be able to determine which molecule would have the greater or the lower boiling point, vapor pressure, surface tension, so forth, based on one, the type of molecule they are, and then from that tells us what intermolecular force they have to deal with, which then we can do the comparison. This here, it's just going to be brief, okay, just to give you, let me clear this up a little bit. There's a thing called the Coulomb's law. It's basically just a measure of the interaction between forces. Like if we have two magnets here together, obviously we all know two magnets coming together, the north and the south interact and they are attracted, okay? And what Coulomb did was come up with an equation that said basically that the force of attraction between two charges is proportional to the magnitude of the charge. Proportion meaning if I increase the charge, I increase the force. But they're inversely proportional to the square of the radius between the two. And so inversely proportional means if I raise one variable, the other variable goes down. But in this case, it goes down by the square of that magnitude. Okay, so you came up with this equation here where the force is equal to KE, which is just a constant. Okay, Q1 and Q2 are the two charges, and then divided by R2, which is the radius between the two. And I want to just quickly demonstrate mathematically what that means by the inversely proportional by the square and how much change it has. Okay, let's take KE, Q1, and Q2 and just put it into one constant. And we'll call that A for right now. We're going to keep it constant. Okay, and so the only thing that's going to vary would be R squared. And so by if we make R equal 1, and let's call it, 1, doesn't make a difference. You just call it 1 nanometer, 1 centimeter, 1 mile. You can make it whatever you want. Just one unit. And so if the force between those two charges, let me write this down here. If we make everything 1 and we keep that constant, we'll call that constant A, where I put Q1, QT, and Q2 and K together. I'm just going to make one constant just to show you. And then we go make R equal 1, and that's R squared, right? Oh, okay, so 1 squared is 1, right? So the force for something that's 1 unit of measure apart is simply A. Everybody agree on that? Okay. Now, let's take those two things, those QA, Q1, and Q2. We're going to move them away from each other. We're going to double the distance from each other. Right now, we started at 1 unit of distance. Now we're going to go to 2 units of distance. And so what now are A stays the same, A, and now we double the R, and that is 2, right? Double 1 is 2. And so 2 squared. And so what has happened to the force? The force now has decreased by a factor of 1/4. Okay, we reduced the force by a quarter by simply doubling the distance. And you see the same thing when you take two magnets, and let's say you put 2 north together or 2 south, and you bring them together, and the closer, if you got them far apart, you don't feel anything, but the closer you bring them together, you can feel that force get stronger. The same is true if you reverse them and just bring north and south magnet together, but don't let them touch. You can feel that force of attraction, and as I move one away, the force decreases, and it decreases drastically. I factor the radius to the square. That's in essence what Coulomb's law is trying to tell you. Okay. So we have this table here, and they're asking you the question: choose the bond or IMF described in each below. Now, the important part here is to read the question carefully. Okay, when you read the question, are they talking about the bond within the molecule, or are they talking about the interaction between molecules, okay, with other molecules? So let's take the first question. It says, what holds the atoms together in one ammonia NH3 molecule? Okay. And so the wording says, what holds the atoms together in one ammonia molecule? So we're talking about the bond. It had nothing to do with other molecules of ammonia, NH3. So we look at the bond of NH3. What type of bond is that? Well, it is a polar covalent bond. Okay. Now, what is holding the sodium ions, keyword sodium ions, in water? That looks like ion dipole, because you're talking about sodium ions, ionic, and water, our aqueous system. And so we're dealing with the ion dipole forces. Third one says, what is holding 3 HCl molecules together? See, so they're not talking about the bond within HCl. They're talking about 3 HCl molecules together. So now we're talking about IMF interactions. And so now you have to determine, is it dipole? Definitely not ion dipole, because there's no ions mentioned here. You got to look at HCl. Is it London dispersion forces? Can't be, right? Because HCl is polar. Okay, so it's not London forces. So now you're left with dipole-dipole hydrogen bridging. Well, take a look at hydrogen bridging. Yes, we got hydrogen there, but hydrogen bridging is only for those that are bonded, only for those hydrogens that are bonded to nitrogen, oxygen, and fluoride. It's bonded to chloride here. So the only choice is dipole-dipole. Okay, so dipole-dipole forces hold 3 hydrochloric acid molecules together. Okay. Now, fourth question. What is holding the ions together in salt, sodium chloride? Okay, so there's no mention here about solution and aqueous system. They're just talking about what is holding the ions together. We're talking about solid sodium chloride. Okay, so now we're talking about the bond for sodium chloride. And sodium chloride is a combination of a metal and non-metal. So the only thing, it's an ionic bond. Okay. Next one, what is holding 4 H2O molecules together? So what is holding 4 water molecules together? Again, we're not talking about the actual bonds of water, H2O. We're talking about 4 molecules that are dispersed someplace. So we're talking about IMF interaction, okay? And so H2O, just put this in long-term memory, it is polar all the time, okay? Water is very polar. Therefore, London forces are not even involved here. So what's left is not ionic dipole, because there's no mention of ions. So you got dipole or hydrogen bridging. Obviously it has a dipole, but we got hydrogen bonded to oxygen. So hydrogen bridging takes precedence. Okay. So hydrogen bridging forces hold these atoms together. What holds nitrogen gas molecules to each other? Okay. To each other. Again, we're not talking about within the molecule, we're talking about inter forces. So that would imply IMF interactions, right? Now they said nitrogen gas is one of the diatomic molecules, have no fear of ice cold beverage, okay? Therefore, we have London dispersion forces. And London forces, it's a nonpolar, nitrogen's nonpolar. Okay, and then finally, but what is holding the oxygens together in an oxygen gas molecule? Read it carefully. We're not talking about, they're not asking about what's happening with other molecules, but within the molecule itself. So what is holding that together? Okay. It's not ionic. It's a covalent bond, specifically a nonpolar covalent bond, because it's diatomic. The two atoms are oxygen, so it makes it nonpolar. Excuse me. And then finally, what is holding two ammonia molecules together? Right. So we got to break it down. Determine ammonia. Ammonia is NH3, like in number 1. Question number 1, they gave you the formula. They're talking about molecules with each other, two ammonia molecules together. So we're talking about IMF interactions. Okay. It's not ion dipole. Eliminate that. It is not London dispersion forces. Why? Because we already established that ammonia is polar. Okay. And to refresh your memory, ammonia, a nitrogen central atom, it's a group 5. And like I stated, group 5 elements, when they're the central atom, will always have a lone pair. Having a lone pair automatically polar molecule. Okay, so you have a polar molecule. So now you're left to determine, is it dipole-dipole or hydrogen bridging? Yes, it's a dipole-dipole. You got dipole-dipole interactions there. However, you have hydrogen bonded to nitrogen, which of those 3 exceptions that you have a stronger force when you have hydrogen bonded to nitrogen, oxygen, or fluoride. And so in this scenario, ammonia has hydrogen bridging forces. Okay. All right. Well, this is basically the type of information that you will be asked to do a compare and contrast. This flow chart kind of breaks it down for you. Okay. That when we're dealing with covalent compounds, we first determine the flow chart's a little bit skewed there. Determine if it's a covalent bond, obviously, 2 non-metals together. Then we determine if it's polar or nonpolar. If it is nonpolar, automatically you don't go any further, London forces, okay? If it's polar, now you have to determine, okay, are we talking about down at the bottom ion dipole? Only if they mention an ionic compound like sodium chloride and water, then ion dipole, plain and simple. Okay. If they don't mention that, then obviously it's not ion dipole. Then you have to discern, is it dipole-dipole, hydrogen bridging? Well, if it's polar, they're all going to have dipole-dipole. However, those hydrogens bonded to nitrogen, oxygen, and fluoride, they have a force that's even stronger than a dipole-dipole interaction. We call that hydrogen bridging, okay? So it's got to be, the hydrogen has to be bonded to the nitrogen or the oxygen or the fluoride, okay? So What I'm going to stop it here, and we'll stop it on slide 20. And next Tuesday, we'll finish it up, knock it out. And I have a few minutes if you want, you have questions. Let me stop this for a second.